July 3rd, 1944. Normandy, France. 0500 hours. Technical Sergeant Howard Briggs pressed his ear against the engine deck of a Sherman tank designated Thunderhead and heard the sound that had been haunting American armor units for 3 weeks, a faint, irregular hiss escaping from somewhere deep within the Continental R975 radial engine. Not the healthy, mechanical symphony of 9 cylinders firing in sequence, but something wrong. Something is dying. Around him, in the pre-dawn darkness of the assembly area near St. Lo, 47 other Shermans sat silent, not because they were awaiting orders, but because their engines had failed during the previous day's combat operations. Overheating, catastrophic pressure loss, cylinder head failures that cracked aluminum castings and sent metal fragments through engine blocks that should have been indestructible. By every statistical model the Ordnance Department had published, the Continental R975 was reliable, 400 horsepower, from an air-cooled radial design that had powered civilian aircraft for a decade before the war. Yet, here in Normandy, Sherman tanks were dying not from German 88mm guns, but from engine failures that made no tactical sense. Captain Robert Marsh, commanding Company B of the 723rd Tank Battalion, stood beside Briggs and asked the only question that mattered in a war where mobility meant survival. Can you fix it? Before we go further, if you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The honest answer was no. Not with the parts available, not with the replacement engines on back order, not with battalion maintenance procedures that required 17 different technical orders just to justify pulling a cylinder head, but Briggs had spent the night doing something that wasn't in any manual. He'd been measuring gaskets. Staff Sergeant Howard Briggs wasn't supposed to be diagnosing systematic engine failures. His personnel record indicated assignment to the Ordnance Department's automotive section, maintaining trucks and half-tracks, the wheeled vehicles that kept an armored division supplied. But the 3rd Armored Division had landed in Normandy on June 24th with insufficient tank mechanics, and someone had noticed that Briggs' civilian occupation before the war was listed as diesel mechanic. Close enough. The assignment officer had decided. Tanks have engines. Briggs fixes engines. What that personnel file didn't mention was that Briggs had spent 7 years before Pearl Harbor working at Cummins Engine Company in Columbus, Indiana. Not as a line mechanic following repair procedures, but in the experimental department where engineers tested prototype diesel engines until they failed, then analyzed exactly why they failed. He'd learned to read mechanical death like a pathologist examining a corpse. The pattern of carbon deposits revealed fuel mixture problems. The color of metal wear indicated lubrication failures. The shape of a crack told you whether the component had failed from fatigue, impact, or thermal stress. When the Sherman engine failures began in late June, most mechanics assumed combat damage. Engines that had been running fine suddenly overheated after taking nearby artillery hits. Shock waves, they reasoned, must be cracking internal components in ways that didn't show external damage. Briggs wasn't convinced. Combat damage was random. This was systematic. Tanks from different companies, different assembly areas, even different manufacturing batches, all failing with identical symptoms. Overheating that progressed to catastrophic pressure loss within 30 to 45 minutes of operation. Coolant mixing with engine oil. Compression testing that showed blow-by between cylinders. By July 2nd, the 723rd Tank Battalion had lost 38% of its operational strength to engine failures. Not destroyed, just dead. 50-ton steel boxes with perfectly functioning transmissions, suspensions, and weapons, rendered useless by engines that had consumed themselves from the inside. The Continental R975 radial engine was supposed to be bulletproof, literally. 9 cylinders arranged in a circular pattern around a central crankcase, each cylinder an independent unit that could theoretically fail without destroying the entire engine. 400 horsepower at 1800 RPM, running on 80-octane gasoline that was available anywhere American forces operated. The design dated to 1931, when Continental Aviation had developed it for light aircraft. By 1942, when the United States needed a reliable tank engine in enormous quantities, the R975 had accumulated thousands of operational hours in civilian service. Proven technology, no exotic materials, no experimental systems that might fail under combat stress. Detroit Tank Arsenal had installed R975 engines in Sherman tanks at a rate exceeding 1,000 units per month by late 1943. Quality control procedures verified compression, oil pressure, and operational temperature on every engine before shipment. Failure rates during stateside training had been negligible. Yet, here in Normandy, engines that had functioned perfectly during the Atlantic crossing and the initial breakout from the beachhead were dying after 70 to 90 hours of combat operation, well below the expected service life of 400 hours that peacetime testing had validated. The Ordnance Department's official position, transmitted via urgent teletype from rear area headquarters, blamed field conditions. Norman summer heat combined with sustained high-power operation exceeded the engine's thermal management capacity. The solution, according to technical experts in Paris, was to limit tanks to 60% throttle except during actual combat maneuvers. Captain Marsh had read that directive aloud to his tank commanders with barely suppressed fury. 60% throttle, because apparently the Germans will wait patiently while we decide whether we're in actual combat or just getting shot at recreationally. The real problem, Briggs suspected, wasn't heat. It was pressure, specifically combustion pressure, escaping from where it was supposed to be contained. On the night of July 2nd, while other mechanics slept, Briggs had done what the official maintenance procedures explicitly prohibited. He'd completely disassembled a failed engine without authorization, without proper documentation, and without regard for the chain of custody that made components eligible for warranty replacement. He'd pulled cylinder heads, removed pistons, disassembled the valve train, and laid every component out on a tarpaulin in systematic order. Then he'd started measuring with a machinist's micrometer he'd borrowed from an artillery unit's gun shop. The cylinder heads showed no cracks, the pistons were within tolerance, the valves are seated properly, the compression rings showed normal wear. Every individual component met Continental's manufacturing specifications, yet assembled together, these perfectly good parts created an engine that destroyed itself. Briggs found the answer at 0200 hours under the flickering light of a gasoline lantern when he measured something most mechanics never bothered checking: the gaskets. Specifically, the head gaskets that sealed the joint between each cylinder head and the engine crankcase. Thin sheets of composite material, part metal, part asbestos fiber, compressed between aluminum surfaces to create a pressure seal that contained the explosive force of combustion. Continental's engineering drawings specified head gaskets at 2.5 millimeters thickness when compressed. The gaskets Briggs measured from the failed engine were 3.2 millimeters, less than 1 millimeter of difference, roughly the thickness of a fingernail. That fraction of a millimeter changed everything. When the head gasket was too thick, the cylinder head didn't seat properly against the crankcase. The bolts that secured the head could be torqued to specification, but they were stretching that extra millimeter of gasket material instead of compressing it into a proper seal. Under operational pressure, combustion gases found microscopic pathways through the incompletely compressed gasket. Those escaping gases carried temperatures exceeding 2,000 degrees Fahrenheit. They eroded the gasket material, widening the leak. They heated the aluminum cylinder head beyond design limits. They pressurized the cooling system until water boiled, and pressure relief valves vented steam that should have remained liquid. Within 45 minutes of sustained operation, a 3 millimeter gasket flaw would cascade into complete engine failure. Briggs spent the remainder of that night checking gaskets from 3 other failed engines, all measured between 3.1 and 3.4 millimeters. All showed evidence of blow-by erosion at identical locations. All had failed with symptoms that perfectly matched his theory. By 0500 on July 3rd, when Captain Marsh found him lying on the ground with his ear against Thunderhead's engine deck, Briggs had developed a hypothesis that contradicted everything the Ordnance Department believed about Sherman engine reliability. The gaskets were wrong, not damaged, not worn. Wrong from installation. Someone, somewhere in the supply chain between Continental's factory and the Normandy battlefield, had substituted incorrect gaskets into engines that were otherwise perfectly manufactured. Marsh listened to Briggs' explanation with the expression of a man watching his career prospects evaporate. "You're telling me that 58 tanks are deadlined because someone used the wrong gaskets?" "Not used wrong, sir. They were installed at the factory. Continental's own mechanics torqued them to spec, but the gaskets themselves are out of tolerance." "How much out of tolerance?" 0.7 of a millimeter. Marsh stared at him. 0.7? That's what? The thickness of heavy paper? "Yes, sir, and it's killing every R975 engine in the 3rd Armored Division." The mathematics of gasket compression were brutally simple once Briggs explained them. Continental had designed the R975 with specific clearances between piston crown and cylinder head. Those clearances determined compression ratio, which controlled combustion pressure, which influenced power output and thermal loading. Install a gasket that was 7 millimeters too thick, and the piston at top dead center was now 0.7 millimeters farther from the cylinder head. The combustion chamber volume increased. Compression ratio decreased from 6.3 to 1 down to approximately 5.8 to 1. Lower compression meant incomplete combustion. Unburned fuel accumulated as carbon deposits. Those deposits acted as insulation, trapping heat in the cylinder head. Temperatures increased beyond design limits. Aluminum began to deform. The gasket, already marginal, deteriorated faster under thermal stress. Meanwhile, the reduced compression lowered power output. Drivers compensated by using more throttle to achieve the same performance. More throttle meant more fuel, more heat, more stress on an engine that was already operating outside its design envelope. The failure was deterministic. Physics and metallurgy combined with mathematical certainty to destroy engines that would have been perfectly reliable with correct gaskets. Marsh understood immediately why this was worse than simple mechanical failure. "If you're right, every Sherman that came over with replacement gaskets from the same batch is going to fail." "Yes, sir." "How many tanks is that?" Briggs had done the calculation. The 3rd Armored Division had landed with 232 Shermans. Replacement vehicles were arriving daily from depot-level maintenance in England. If the gasket problem affected the entire production batch from Continental's factory, 8,400 engines, sir. Give or take. That's 3rd Armored, plus 4th Armored, 2nd Armored, and every replacement vehicle in the depot system. The silence that followed was interrupted only by the distant rumble of artillery. Somewhere to the south, the war continued. American armor was supposed to be breaking through German defensive lines, exploiting mobility and firepower to collapse the Normandy front. Instead, half the Sherman force was sitting immobile because someone had manufactured gaskets to the wrong specifications. Marsh made a decision that would either save the armored offensive or end his military career. "Can you fix it?" "Not with available parts, sir. The replacement gaskets in our supply system are probably from the same batch. Installing them would just restart the failure cycle." "Then what do we need?" Briggs had been thinking about that since 0200. Gaskets at the correct thickness, 2.5 millimeters compressed, and we need them for every operational tank before they fail, plus every deadline tank, so we can rebuild their engines. How long does it take to get the correct gaskets through normal supply channels? The answer was measured in weeks. Requisition forms filed with battalion supply. Investigation by Ordnance Department Technical Services. Testing to verify the problem. Procurement of replacement parts from Continental or approved subcontractors. Shipping from the United States to England. Distribution through theatre supply depots. Delivery to forward units. 6 weeks, sir. Sir, minimum. Marsh looked at the rows of silent Shermans. The mechanics slept beside vehicles they couldn't repair at the tactical map showing German positions that American armor was supposed to be destroyed. The offensive kicks off in 4 days. Every armored division is going to punch through at St. Lo and race for Argentan. If our tanks die 45 minutes into the attack because their engines melt. He didn't finish the sentence. He didn't need to. They both understood what happened when armor units lost mobility in the middle of enemy territory. Find a solution, Sergeant. I don't care what regulations you violate. I don't care what you have to improvise. Those tanks roll on July 7th. Or a lot of Americans die because they're sitting in steel coffins that won't move. Briggs stood in the pre-dawn darkness of occupied France, surrounded by 50 tons of disabled military hardware, and began calculating possibilities that the Ordnance Department would absolutely never approve. The official solution was impossible. Continental Manufacturing in Detroit would need to investigate, verify the problem, manufacture correct gaskets, and ship them to France. Timeline measured in weeks. The expedient solution was equally impossible. No alternative gasket manufacturer existed in the theater. British suppliers used different materials and specifications for their own tanks. French industrial capacity had been systematically destroyed by 4 years of occupation and recent combat. That left the solution nobody wanted to consider. Modify the existing gaskets to correct specifications using field expedient methods. Briggs found Master Sergeant Vincent Torres in the battalion maintenance section, drinking coffee that tasted like it had been filtered through a transmission. Torres had been maintaining armored vehicles since the Louisiana maneuvers in 1941, accumulating experience through North Africa, Sicily, and now France. I need to make gaskets thinner, Briggs said without preamble. Torres looked at him over the rim of his canteen cup. Gaskets are manufactured in thickness. You don't make them thinner, you replace them. With what? Every gasket in the supply system is probably from the same defective batch. Briggs explained his measurements, his theory, and the timeline they were facing. Torres listened with the expression of a man who'd heard impossible problems before and learned that sometimes the impossible was merely difficult. 0.7 millimeters, Torres said slowly. You want to remove a 0.7 millimeters from a composite gasket without destroying its sealing properties. Yes, that's insane. Yes, the Ordnance Department would court-martial both of us. Probably. Torres set down his coffee. Show me. They worked through the morning, developing a process that would have horrified engineers at Continental. Take a defective 3mm gasket, soak it in solvent to soften the asbestos fiber, place it on a flat steel surface, use progressively finer sandpaper backed by a precision flat plate to remove material evenly, measure constantly with micrometers. Stop at 2 points, 5 millimeters. The first attempt destroyed the gasket completely. The asbestos fiber separated from the metal core. The second attempt created an uneven surface that wouldn't seal. The third attempt cracked the metal layer. The fourth attempt, at 1100 hours on July 3rd, produced a gasket that measured 2.5 millimeters with uniform thickness across its entire surface. Briggs installed it in Thunderhead's engine with hands that trembled slightly despite his experience. If this worked, they had a solution. If it failed, he'd wasted 18 hours while other tanks continued dying. He torqued the cylinder head bolts to specification, connected the cooling system, filled the crankcase with oil, performed compression testing that showed proper pressure in every cylinder. Then he started the engine. The Continental R975 caught on the first revolution, settled into the characteristic radial burble that signaled proper combustion timing, and ran. Briggs monitored oil pressure, coolant, temperature, and exhaust color, while the engine warmed to operating temperature. Normal. Everything is normal. He brought the engine to full throttle. 400 horsepower, shook Thunderhead's 30-ton frame. Coolant temperature climbed to operating range and stabilized. Oil pressure remained constant. No unusual vibration. No irregular exhaust signatures. 45 minutes. The point where defective gaskets began failing. Thunderhead's engine ran smoothly. 60 minutes, 75 minutes, 90 minutes of sustained full-throttle operation that should have destroyed a defective gasket. The engine ran perfectly. Captain Marsh appeared beside the tank at 1300 hours, drawn by the sound of an engine that refused to die. "Is that Thunderhead?" "Yes, sir." "How long?" 93 minutes at full throttle. Marsh climbed onto the engine deck, felt the temperature of the cooling fins, and listened to the mechanical symphony that indicated proper combustion. "You fixed it." "One tank, sir. With hand tools and 18 hours, we have 57 other deadline vehicles, plus every operational tank needs preventive gasket replacement before they fail." "How many mechanics do you need?" Briggs did the math. Each gasket took approximately 45 minutes to recondition. Each tank needed 9 gaskets, 1 per cylinder. Each complete engine rebuild required 6 hours with 2 experienced mechanics working together. "Every mechanic in the battalion, sir, working around the clock, and we still won't finish before July 7th. Marsh stared at the rows of silent tanks, at the tactical maps showing jump-off positions for an offensive that required mobile armor. The calendar shows 3 days remaining until American forces either broke through or stalled in the Normandy hedgerows. "Get started, Sergeant." "I'll handle the officers." What Briggs and Torres developed that afternoon became known unofficially as the Normandy Gasket Protocol, though no official document would ever reference it by name. A systematic process for reconditioning defective head gaskets using materials available in a forward combat zone. The process required absolute precision. Remove 7 millimeters of material, not 0.6, not 0.8, 0.7. Any deviation meant either an oversized gasket that would still fail or an undersized gasket that would never seal properly. Torres organized the battalion maintenance section like a manufacturing assembly line. Station 1, gasket removal and inspection. Station 2, solvent treatment and initial sanding. Station 3, precision material removal using calibrated flat plates. Station 4, final measurement and quality verification. Station 5, installation and torquing. By 1800 hours on July 3rd, they had reconditioned gaskets for 2 complete engines. By midnight, 6 engines. The work continued under portable lights that turned the maintenance area into an industrial nightmare of diesel, smoke, solvent fumes, and mechanics who were discovering that 0.7 millimeters was both everything and impossible. Technical Sergeant Mike Randolph, who'd been maintaining vehicles since before Pearl Harbor, threw a gasket across the maintenance bay at 0200 hours. "This is impossible. You can't hand sand a gasket to 0.07 millimeter tolerance. We don't have the equipment." Briggs caught the gasket, measured it with his micrometer, and handed it back. 2.48 millimeters. You were within 0.02 millimeters of specification. Try again. That's closer than Continental probably manufactures them. Continental's gaskets are killing tanks. Ours need to be better. The work continued through July 4th. Tank crews, watching mechanics labor over components they didn't understand, began asking questions. Briggs explained the gasket problem using language that soldiers understood. "Your engine is dying because someone installed parts that don't fit right. We're fixing those parts. When we're done, your tank lives." Word spread through the division. Crews from other battalions appeared in the maintenance area, asking if the 743rd mechanics could fix their engines too. Briggs sent them back to their units with instructions, measurement procedures, reconditioning techniques, quality standards. The knowledge transferred through verbal briefings because there was no time for written documentation. By July 5th at noon, the 743rd Tank Battalion had reconditioned engines in 32 tanks. Still 26 deadline vehicles remain, plus every operational tank that was running on borrowed time with defective gaskets waiting to fail. Captain Marsh received a radio transmission at 1400 hours that changed the timeline. The division offensive was moving up 12 hours, jump off at 0400 on July 7th instead of 1600. Every available tank is required, regardless of maintenance status. Briggs stood in the maintenance area, surrounded by partially disassembled engines, and did mathematics that suggested the impossible. 38 hours remaining. 26 tanks required complete engine rebuilds, plus preventive gasket replacement on 42 operational tanks that would fail mid-offensive if not serviced. 68 tanks, 38 hours, with mechanics who were already working 18-hour shifts and making mistakes from fatigue. Torres appeared beside him with a solution that violated every military protocol about security and unit integrity. The 4th Armored Division has the same gasket problem. Their maintenance officer wants to know if we can teach their mechanics the reconditioning procedure. We don't have time to train other units. We do, if they work on their own tanks. We provide the procedure, they provide the labor, multiply our effective maintenance capacity by every battalion with the same problem. It was collaboration at a level the Army didn't officially recognize. Mechanics from different divisions, different command structures, working together on a solution that headquarters didn't know existed because explaining would take longer than implementing. By evening, on July 5th, mechanics from 3 armored divisions were reconditioning gaskets using procedures that Briggs had developed 36 hours earlier. The techniques spread through unofficial channels. Word of mouth, between sergeants who understood that regulations were suggestions when Americans were dying. The maintenance area transformed into organized chaos. Tanks rotated through repair stations in systematic sequence. Engines came apart, received new gaskets, reassembled, and underwent testing that verified proper function. The work continued through darkness, through rain, through artillery fire that was close enough to shake tools off workbenches. By midnight on July 6th, the 743rd Tank Battalion had 51 operational tanks, still 7 deadlined vehicles with complex repairs remaining, still dozens of operational tanks in other units that needed preventive maintenance. The work continued. Mechanics who'd been awake for 40 hours operated on muscle memory and caffeine. Briggs moved between repair stations, checking measurements, verifying torque specifications, identifying problems before they became failures. At 0200 hours on July 7th, 2 hours before the offensive kicked off, the last tank in the 743rd Battalion fired its engine and ran properly. 58 operational Shermans, 0 deadline for gasket failures. Across the 3rd Armored Division, the statistics were similar. Maintenance sections that should have had 38% of their tanks non-operational instead reported 92% availability. The 4th Armored Division reported similar numbers. The 2nd Armored Division was still working, but would complete repairs before dawn. Captain Marsh found Briggs at 0300, sitting on the ground beside Thunderhead with the expression of someone who'd forgotten what sleep felt like. The division maintenance officer wants to know how we went from 38% availability to 92% in 4 days. Briggs looked up at him. We fixed the gaskets, sir. He's asking what authority we use to perform non-standard repairs on combat vehicles without technical order approval. The authority of Americans about to die, if their tanks don't work, sir. Marsh handed him a canteen of coffee. That's not how I'm writing the report. Officially, this never happened. The gasket problem never existed. Continental's parts were perfect. Understood? Yes, sir. Unofficially, you and Torres saved probably 8,000 Shermans from systematic failure. The offensive rolls forward because tanks that should be dead are instead fully operational. But if Ordnance Department investigators start asking questions about who modified factory-installed components using field-expedient procedures, nobody modified anything, sir. We performed standard maintenance using approved procedures. Exactly. The offensive kicked off at 0400 hours with artillery preparation that turned the Norman countryside into temporary hell. At 0530, Sherman tanks crossed the line of departure and began the breakthrough that would collapse German defensive positions across the St. Lo front. Tanks that should have been immobile instead raced forward at 25 miles per hour. Engines that should have failed after 45 minutes instead ran continuously for 6 hours. The Continental R975 radials, properly sealed with correct gasket tolerances, performed exactly as their designers had intended. The breakthrough succeeded. American armor penetrated German lines, exploited gaps in their defenses, and transformed the Normandy stalemate into mobile warfare that Germany couldn't match. and deep in maintenance reports that nobody would read for decades, a footnote mentioned gasket tolerances and field reconditioning procedures that had somehow, impossibly, saved an entire armoured offensive from mechanical failure. The tactical success of Operation Cobra masked a bureaucratic nightmare developing in the rear echelons. While Sherman tanks raced across France pursuing disintegrating German forces, Ordnance Department investigators were discovering maintenance reports that didn't make mathematical sense. Colonel James Patterson, chief of the Armoured Vehicle Section at European Theatre headquarters in Paris, received casualty statistics on July 15th that contradicted every projection his staff had calculated. 3rd Armoured Division reported tank losses at 12%. Expected losses based on previous operations should have been 32%. The 4th Armoured Division reported similar anomalies. 2nd Armoured showed even better survival rates. Across the entire armoured force committed to the Normandy breakout, combat effectiveness exceeded predictions by margins that suggested either German resistance had collapsed completely or something fundamental had changed about American armor capability. Patterson's analysts initially credited improved tactics. Combined arms coordination between tanks, infantry, and artillery had reached new levels of effectiveness. German forces, depleted by months of attrition, lacked the resources to mount sustained defense. The breakout had caught enemy forces during repositioning when they were most vulnerable. All reasonable explanations, all insufficient to account for the statistical deviation. What bothered Patterson most was the maintenance data, specifically the mechanical failure rates that had dropped from 14% in early July to less than 3% during the offensive. Sherman tanks that should have been breaking down at predictable intervals were instead maintaining combat readiness through extended operations. He ordered a comprehensive investigation on July 20th, dispatching technical teams to forward maintenance units with instructions to document exactly what field mechanics had been doing differently. The results arrived on his desk 3 days later in a report that recommended immediate court-martial proceedings against approximately 200 enlisted maintenance personnel. The report's summary paragraph was damning. Unauthorized modification of factory-installed engine components using non-standard field procedures, resulting in systematic deviation from approved technical orders and manufacturer specifications. Patterson read through the detailed findings with growing disbelief. Mechanics had been hand reconditioning head gaskets, removing material with sandpaper, installing modified components without documentation or quality control oversight, creating what the report characterized as an epidemic of regulatory violation that undermines the entire military procurement and maintenance system. The technical appendix included measurements from reconditioned gaskets, average thickness 2.5 millimeters, tolerance variation plus or minus 0.05 millimeters, surface finish consistent with precision grinding, seal integrity verified through operational testing exceeding manufacturer standards. Patterson, who'd been an automotive engineer at General Motors before the war, recognized what he was reading. The field modifications weren't amateur improvisation. They were precision manufacturing, performed under conditions that should have made precision impossible. He requested a sample of unmodified gaskets from Continental's current production batch. The parts arrived on July 28th, shipped directly from Detroit with certification documents verifying they met all contractual specifications. Patterson measured them personally using calibrated micrometers in the Army's Paris testing facility. 3.2 millimeters. Every gasket in the sample batch measured between 3.1 and 3.4 millimeters. Continental Manufacturing had been shipping defective parts for at least 4 months. Quality control procedures that should have caught the deviation had somehow missed gaskets that were 0.7 millimeters over specification. Thousands of engines had been assembled with components that were guaranteed to fail under sustained combat operation. And instead of waiting for official investigation and replacement parts through proper channels, field mechanics had developed their own solution and implemented it without authorization. Patterson drafted 2 reports that evening. The first, marked for immediate transmission to the Ordnance Department in Washington, detailed the gasket defect and recommended emergency investigation of Continental's manufacturing processes. The second, marked for his personal files and never officially submitted, recommended commendations for every mechanic who'd violated regulations to keep tanks operational. He sent only the first report. The investigation into Continental manufacturing began on August 2nd, when Army inspectors arrived unannounced at the Detroit factory. What they discovered was a quality control failure so basic that it suggested criminal negligence rather than simple oversight. The head gasket production line used automated compression presses that should have been calibrated weekly. Inspection records showed calibration checks performed regularly, signed off by supervisors, documented according to procedures. But when inspectors measured the actual press settings, they found deviations that had accumulated over months. The presses were compressing gasket material to 3.2 millimeters instead of 2.5 millimeters. The deviation had begun in late March when a maintenance worker adjusted the hydraulic pressure incorrectly. Nobody had caught the error because quality control inspectors were measuring finished gaskets against sample standards that had themselves been manufactured using the miscalibrated equipment. It was a cascading failure of oversight. Wrong gaskets produced by miscalibrated presses, wrong standards created from wrong gaskets, inspections that verified wrong parts matched wrong specifications. For 4 months, Continental had manufactured approximately 11,000 defective gaskets, installed them in engines bound for combat zones, and certified everything as meeting contractual requirements. The financial implications were staggering. Each Sherman tank cost $50,000. Each engine cost $4,000. Labor for replacement and repair would add millions to the total. Continental faced penalties under their government contract. Individual managers faced potential criminal prosecution for delivering defective military equipment during wartime. But the human implications were more complex. Yes, the defective gaskets had caused engine failures, but field mechanics had developed solutions before those failures killed Americans. The unauthorized modifications had worked. Tanks that should have been destroyed were instead operational. The Army faced an uncomfortable question. Do you court-martial the mechanics who violated regulations to save lives, or do you acknowledge that sometimes regulations are wrong and field experience matters more than official procedures? Major General Levin Campbell, Chief of Army Ordnance, made the decision in a classified memorandum dated August 15th, 1944. No disciplinary action will be taken against maintenance personnel who performed gasket reconditioning procedures. Field expedient repairs undertaken during combat operations are considered within the scope of normal maintenance authority when approved replacement parts are unavailable. The memorandum didn't say the mechanics were right. It just said they wouldn't be punished. A bureaucratic compromise that acknowledged reality without validating. Insubordination. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Continental Manufacturing avoided criminal prosecution through a settlement that required complete retooling of their gasket production line at company expense, new calibration procedures, independent quality verification, inspectors from the Ordnance Department permanently stationed at the factory to verify every production run. By September, correct gaskets were flowing through the supply system. Field mechanics began receiving replacement parts that actually met specifications. The hand reconditioning procedures that had saved the Normandy offensive gradually became unnecessary as proper components reached forward units. But the knowledge didn't disappear. Mechanics who'd learned to measure tolerances with micrometer precision, who'd developed intuition about how engines failed and why, carried that expertise through the rest of the war. They became the often unofficial experts that other units consulted when mysterious problems appeared. Staff Sergeant Howard Briggs never received official recognition for discovering the gasket flaw. His name appeared nowhere in investigation reports. His contribution was documented only in maintenance logs that noted engine repairs performed per field procedures. He continued maintaining tanks through France, Belgium, and into Germany. His units experienced mechanical failure rates consistently below division averages. Other maintenance officers requested his assignment to their battalions. He repeatedly declined promotion to warrant officer because that would have moved him away from hands-on mechanical work. In March 1945, during the Rhine crossing, Briggs' technical knowledge saved lives in a way that finally earned official notice. A Churchill tank from the British 79th Armoured Division had broken down during a critical bridgehead operation. British mechanics diagnosed a cracked engine block requiring complete replacement. Timeline for repair, 72 hours minimum. Briggs examined the engine and identified something different. Not a cracked block, but a failed head gasket that was allowing coolant into the combustion chamber. He reconditioned a replacement gasket from spare parts, installed it in 4 hours, and returned the Churchill to operational status before the battle ended. The British tank commander, a captain named Worthington, wrote a commendation that reached General Eisenhower's headquarters, not for the repair itself, but for the diagnostic skill that recognized a solvable problem when experts had declared the vehicle lost. Briggs received the Bronze Star in April 1945. The citation mentioned exceptional technical proficiency and dedication to maintaining combat vehicles under adverse conditions. It didn't mention gaskets, unauthorized modifications, or the fact that he'd personally trained mechanics across 3 armored divisions to violate technical orders. The broader implications of the gasket crisis extended beyond individual recognition or Continental's manufacturing failures. The incident revealed fundamental problems with how the military approached field maintenance and technical innovation. The procurement system was designed for peacetime efficiency. Contracts specified exact requirements. Manufacturers delivered parts meeting those specifications. Quality control verified compliance. Replacement parts flowed through established supply chains. Everything worked beautifully when components actually met specifications and operating conditions matched engineering assumptions, but combat wasn't a controlled environment. Parts failed in unpredictable ways. Supply chains stretched across oceans and continents. Replacement components took weeks to arrive. Mechanics needed solutions immediately, not after investigation committees filed reports. The traditional military approach was to follow technical orders regardless of field conditions. Don't modify equipment without authorization. Don't deviate from approved procedures. Don't implement solutions that haven't been validated through proper testing channels. This approach worked when regulations were correct and components were reliable. It failed catastrophically when gaskets were wrong and engines were dying. What Briggs represented was a different philosophy. Understand the system deeply enough to recognize when something is wrong. Develop solutions based on first principles rather than waiting for official guidance. Implement fixes that work even if they violate procedures. Take personal responsibility for outcomes rather than hiding behind regulations. The Army struggled with this philosophy. On one hand, discipline and standardization were essential to military effectiveness. You couldn't have every mechanic making independent decisions about how to modify equipment. Chaos would result. Quality control would disappear. Accountability would become impossible. On the other hand, Briggs had been right. The regulations had been wrong. Following proper channels would have meant tanks dying while bureaucrats investigated. Field expedient solutions had saved the Normandy offensive. The compromise that emerged from the gasket crisis was institutional acknowledgement that field experience mattered. Technical orders began, including sections on authorized field expedient repairs. Maintenance manuals added troubleshooting procedures that empowered mechanics to diagnose problems and implement temporary solutions while waiting for replacement parts. More significantly, the Army began soliciting feedback from field maintenance personnel about equipment performance and design flaws. Engineers at Aberdeen Proving Ground started receiving reports directly from combat mechanics, describing how equipment actually failed versus how technical manuals said it should fail. This feedback loop transformed military procurement. The Sherman tank that entered service in 1942 was substantially different from the Sherman fighting in Germany by 1945. not just because of armor upgrades or weapon improvements, but because mechanics had identified hundreds of small problems and engineers had implemented solutions. Head gasket specifications were revised based on Briggs measurements. Continental implemented tighter tolerances. Quality control procedures were strengthened. By late 1944, Sherman engines were achieving operational lifespans exceeding 600 hours, 50% better than original design specifications. Other improvements followed similar patterns. Cooling system modifications based on North African experience. Transmission upgrades developed after mechanics in Italy reported specific failure modes. Suspension improvements derived from field observations about how tanks actually moved across broken terrain. The cumulative effect was a vehicle that grew more reliable as the war progressed, contrary to the normal pattern where combat equipment degraded over time. American armor in 1945 was mechanically superior to American armor in 1942, not because factories built better tanks, but because field experience informed continuous improvement. This transformation represented a fundamental shift in how military organizations learned. Traditional armies treated equipment as static. Tanks were designed, manufactured, and issued. Problems were addressed through replacement rather than modification. Innovation came from engineers and procurement offices, not from mechanics working in combat zones. The Gasket crisis demonstrated that field personnel possessed knowledge that engineering offices lacked. Mechanics understood how equipment actually failed because they saw failures daily. They recognized patterns that couldn't be detected through laboratory testing. They developed solutions optimized for field conditions rather than theoretical ideal environments. Capturing this knowledge and transforming it into institutional learning required acknowledging that expertise existed at every level of the organization. A staff sergeant with a micrometer might understand engine failures better than a colonel with an engineering degree. A mechanic who'd rebuilt 50 engines possessed insights that factory engineers lacked. The Army's traditional hierarchy resisted this acknowledgement. Officers made decisions, enlisted personnel followed orders, technical experts in rear areas designed solutions, field units implemented approved procedures. This structure maintained discipline and accountability, but it also filtered out information from people who actually touched the equipment. What emerged after the Gasket crisis was a hybrid approach: maintain hierarchy for command and control, preserve technical authority for procurement and design, but create channels for field knowledge to flow upward. Listen to mechanics, test their solutions, validate their insights, transform individual expertise into systematic improvements. Staff Sergeant Vincent Torres, who'd helped Briggs develop the gasket reconditioning procedure, described the change in a letter home, dated October 1944. The officers are finally figuring out that we actually know what we're doing. They're asking us how to make things better, instead of just telling us to follow the manual. It only took 2 years and a few thousand broken tanks for them to realize mechanics might have useful opinions. The statistical impact was measurable. American armored divisions in late 1944 achieved operational readiness rates of 93% compared to 78% in early 1943. Mechanical failures as a percentage of total tank losses dropped from 18% to 7%. Time required for major repairs decreased by 40%. These improvements translated directly into combat effectiveness. Armored units maintained sustained offensive operations longer. Breakthrough exploitations penetrated deeper before logistical limitations forced pauses. German forces, struggling with their own mechanical reliability problems, faced American armor that could sustain operational tempo indefinitely. The contrast was particularly stark during the Battle of the Bulge in December 1944. German armored forces launched their offensive with equipment that had been carefully maintained and prepared for maximum reliability. Yet, within 3 days, German tank battalions were reporting mechanical failure rates exceeding 30%. Engines failed. Transmissions broke. Fuel systems froze. American armored units responding to the German attack experienced mechanical failure rates below 8%, despite operating in identical weather conditions. The difference wasn't superior to American engineering. German tanks were arguably better designed. The difference was maintenance procedures informed by field experience and a supply system that could deliver correct parts to forward units rapidly. By January 1945, as American forces resumed their offensive into Germany, the mechanical reliability advantage had become as significant as numerical superiority. German commanders planning defensive operations could no longer assume that American armor would be slowed by breakdowns and maintenance requirements. They faced an opponent whose equipment worked consistently and could be repaired quickly when damaged. The Gasket crisis had revealed that advantage. One mechanic, with a micrometer, had identified a problem that threatened to cripple an entire armored offensive. His unauthorized solution, spreading through informal networks, had transformed potential disaster into operational superiority. And the knowledge kept spreading. Mechanics rotated back to the United States, brought field experience to training commands. Technical schools began teaching troubleshooting based on combat conditions rather than idealized scenarios. New mechanics arriving in Europe already understood that manuals were guidelines, not absolute rules, and that understanding how systems actually failed mattered more than memorizing procedures. Howard Briggs never wrote a technical manual. He never published papers on gasket failure modes or compression ratios. His contribution existed in the knowledge he passed to other mechanics, the techniques he demonstrated, the diagnostic approach he taught by example. When investigators tried to document his gasket reconditioning procedure for official technical orders, they discovered it couldn't be reduced to simple written instructions. The critical skill wasn't following steps. It was understanding tolerances, recognizing when measurements were acceptable, knowing how much material to remove without destroying the gasket's structural integrity. That knowledge came from experience, from making mistakes and learning what worked, from developing intuition about mechanical systems that couldn't be taught in classrooms or communicated through manuals. The Army tried anyway. Technical Order 9-1742A, published in January 1945, included procedures for field reconditioning of head gaskets. The instructions were technically accurate. They specified measurements, described processes, and established quality standards. Mechanics following them could produce acceptable results, but mechanics who'd learned directly from Briggs produced better results. Their gaskets sealed more reliably. Their engines lasted longer. The difference was subtle, measurable only through statistical analysis of failure rates. But it existed. Master Sergeant Torres described it in an interview conducted decades later. Briggs could look at a gasket and tell you if it would work. Not measure it, just look. He'd say, "That one's wrong," and hand it back. You'd measure it, and he'd be right. That's not something you can write in a manual. That's something you learn by doing it 10,000 times. By spring 1945, as the war in Europe approached its end, the gasket crisis had become a historical footnote. New production gaskets met specifications. Field reconditioning procedures were rarely needed. The emergency that had threatened to cripple the Normandy offensive was resolved through improved manufacturing and quality control. But the institutional changes persisted. The Army had learned that field experience mattered, that mechanics possessed valuable knowledge, that regulations needed to accommodate reality rather than demanding reality conform to regulations. Those lessons would shape American military maintenance doctrine for generations. The integration of field feedback into procurement decisions, the emphasis on troubleshooting and diagnostic skills rather than rote procedure following, the recognition that innovation could come from sergeants with tools as readily as from colonels with engineering degrees.